A very good afternoon to one and all present here. I once again welcome you all in the ninth day of International Training Cum Certificate course on Precision Agriculture. We have with us our guest speaker, Professor Rajiv Sinha sir. As sir has already given a lecture yesterday on the topic of precision agriculture, remote sensing, uh, today he will be just forwarding the same topic and explaining how we can process the data to get a well processed data that would be used in the field by the farmers as well by the scientists. So I request sir to continue with his lecture. So over to you, sir. I humbly request Professor Dr. Rajiv Sinha sir. Sir, am I audible right there? Rohit sir, Sinha sir is here or not?
हाँ हाँ प्रेजेंट है सर, को होस्ट भी है, हो सकता है कि कोई टेक्निकल ग्लिच हो, मैं बात कर लेता हूँ एक बार.
Okay, sir.
सर मेरी आवाज आ रही है आपको?
Okay, good evening, everyone.
नमस्कार सर, नमस्कार. आप विजिबल हैं
So
और
let's
ऑडिबल?
start the lecture
yes,
today.
sir, yes.
I hope it's okay, Ankur and Jyoti.
प्लीज सर, प्लीज स्टार्ट करिए.
Yes, sir. Yes, sir.
हाँ, यस सर, यस सर.
All right, so let's start the lecture today. And yesterday, I introduced you to the basic concepts of remote sensing, and I tried to explain how the remote sensing data sets are collected, what sort of data set we are looking at, what are the different platforms and sensors. Today, I'm going to talk about how that kind of a data is actually processed, because remember that the data which is acquired from the satellites are not the ready to use products. Okay, so you have to process it. There are certain enhancement and there are certain processing techniques which are involved to process that data. So those who are not familiar with the digital image processing techniques, they might find it a little overwhelming, but don't worry. This is something which I teach. This particular lecture, I would normally cover in something like 6 or 7 lectures. So it's always a challenge to cover this in just one lecture. But the idea is not to make you an expert in digital image processing. The idea is to make you aware of what sort of technology and tools are available with us. And then, you can always follow it up. There are always opportunities for doing a much more detailed course on that. But I think today, if you could only appreciate what is the power of the image processing, tools and techniques, and what all we can get out of that, I think that will serve the purpose. So don't worry about I will show you some slides where some equations and some mathematics are involved, but I wouldn't worry too much about that for now. So let's start. Now the idea is, if you remember, we talked about yesterday about the remote sensing satellites, and I mentioned to you that there are three different types: geosynchronous, which is where the orbital period is synchronous with the rotational period of the Earth; geostationary, when the orbits are in the same direction and with the same speed at their rotation, and therefore these satellites will remain or will appear to be stationary with respect to the Earth. And that is quite useful for many applications. And then there are sun synchronous, where the satellite will cross the equator at the same local time every day. I also explained that each of these satellites have their own utilities and applications. So if you look at the right-hand side diagram, this is how the paths of the satellites will appear on different different cycles. So basically, because the Earth is rotating, every time the satellite crosses or completes one particular rotation of the Earth, it will cover a different part of the Earth, and that's how the entire Earth is actually covered. You can see 1 to 11, and then of course 12, 13, 14, etc., and so on. And there'll be, at some point of time, the satellite will cross the same path, almost the same path, around the same time. So that is how it is designed. So therefore, every satellite will have its own cycle, which is also called the orbital period, and then each satellite, depending upon its altitude and its resolution, will have its own swath, path, and row. So if you look at the same map on a two-dimensional form, you will basically see something like that. So each of these days, day 1 to day 22, is basically shown by a line, which is basically a path of the satellite. Each time the satellite is passing through different parts of the and you can see a sketch of the outline of the India map, and therefore you can figure out which part of India will be covered on which day of the satellite. So these things are already known. So we know that which part of the world will be crossed by which satellite and at what time. And then you can see that after day 22, the day 1 starts again, and then it will basically come back to the same point. So that's how it works basically, right? Now, so if you go further, from here, and if you look at a particular satellite data, then each satellite data will have will be divided into different kinds of pixels, which is again as determined by the resolution of the satellite image and sensors. So if you remember, we talked about the pixels yesterday. So each data, each image which is satellite is actually acquiring is basically in the raster form, and so therefore a raster data means that the data set will have a row and a column, and each row and column, or each pixel, which is something like this, is defined by the size of this pixel is defined by the resolution of the image here, right? So therefore, so you can actually locate. Each pixel will have an address in terms of the row number and in terms of the column number. So this is basically, for example, this is a column. So this is basically the first row and third column, for example, and so on. So that's how it is basically designed. And then if you remember, we also talked about the fact that the data is collected in multispectral, format, which means that each band, if you remember, we also talked about the atmospheric windows yesterday, and based on the atmospheric windows, we design how many bands in which the satellite data will be collected. So this kind of data is actually being collected in each band separately. So you will basically have a stack of the data in the form of the number of bands of the data which the sensor is supposed to be collecting. So basically, you have each image will have rows and columns, and then there will be layers of data depending upon how many bands the data is being collected in. Okay, now once the data is collected, the data has lots of error. There are radiometric errors which are possibly a function of the sensor. There are geometric errors because of the different kinds of distortions. Even though satellite is flowing at a very high elevation, even then there are geometric errors because Earth is not obviously a flat object. It has a curvature. Then there are also issues related to georeferencing. The satellite is providing some location of to the data set, but we still have to make them much more precise. So there are these errors which have to be corrected. Most of the time, these errors are already corrected when the data is supplied to you, but I will go through them very quickly just to make you aware that what are the kind of errors which are there and how it is corrected. Then, the data product is generally provided as either as a photo product, so you can get an image of the area, or you can get a digital data. Earlier times, they were only providing us the photo product generally, but now it's the digital data is actually much more common because then we can process the data and then we can create products of our choice, for example. So I'll talk about some of those products as we go along. Now, this is how, for example, a digital image will look like. Okay, so you can see this is an image of Kanpur area. We can see the Unnao is here, our IIT campus is somewhere here, Bitur is here, and so on. Now, if you look at it, this looks like a photograph, right? But remember, this is not a photograph. How this kind of image has been generated, we'll talk about that in the next few slides. But practically speaking, this entire image is nothing but an array of numbers. Okay, so basically, it actually looks like this. So this is basically, this image is nothing but a raster of 2D array of the numbers, and you can now see that I've overlaid a grid on the top of that. So each grid is basically a pixel, and each pixel has a value, which is basically the reflectance value of that particular pixel, and the size of the pixel, as I said before, is determined by the spatial resolution of the data. Okay, and the value of each pixel is basically called a digital number. Okay, so what we do in digital image processing, that we try to manipulate these digital numbers, we extrapolate, interpolate, we multiply, we add, and so on. So all of these processes we'll talk about, and then we try to enhance the original data and to make them more better in terms of the interpretations. Right. Remember also that we are talking about multi-layer data. So there are multispectral images. So there are different bands of data which are stacked on top of each other. And then there are also elevation, data sometimes is available, from other satellite data sets. So you can combine all of these data sets into one layer and create images like this at some point of time. So we'll talk about that. So the original image, as I said, might have a very limited range of DN values. So you can, if you plot the histogram of the original data, it might look like that, for example. So even though the sensor had the capability of capturing the data in a very large range of radiometric resolution, let's say 0 to 255, it is the data is located in a very small range. So therefore, the information which is available for a particular area is very much condensed. So we may have to do some processing to enhance the data set. And these are the different kinds of processing technique which we use. So there are radiometric image corrections, there are radiometric, geometric image corrections. There are various types of image enhancements which we do, image filtering, transformation, color enhancement, image fusion, multidimensional visualization, image segmentation. So lots of processing techniques are involved. So I'll, give you a very quick overview of these processing techniques. But as I said, these are, this can form a full-fledged course, for example, at some point of time. So let's go through these. So let's talk about the geometry corrections first. As I said, all remote sensing data are subjected to some sort of geometric distortion. And these are caused by various factors. These are, caused by certain changes in the satellite positions, pitch, roll, and yaw. There are, there are also some of them are related to the topography. Some of them are related to some other undulations and so on. So there are some times which are related to the satellite and sensor related stuff. Sometimes they're related to the Earth's undulations and so on. And all of these geometric errors have to be corrected before you start using it. So the idea is that we would like these data sets, these images, to represent the Earth's surface, in the most accurate way as much as possible. Okay, that's one thing. The second thing is that we also have to register the geometry, these images to a known coordinate system, because we are used to a coordinate system, for example, lat long coordinate, for example, or sometimes people also use UTM coordinates and so on. So all of these images have to be registered to some sort of a ground coordinate system. So before you assign the coordinate system, you have to also, first of all, geometrically correct the images as well. So these are what we do. So there are some examples here which are which can explain why and how these image distortions are produced. Now, there are many factors because of which the distortions can happen in the images. They can be related to perspective of the sensor optics. They can be related to the motion of the scanning system, platforms, platform altitude and velocity, terrain relief, for example, curvature and rotation of the Earth, and so on. So you can see that there are, so there are two types of distortion we talk about. One is the non-systematic errors or non-systematic distortions, which cannot be modeled and corrected because they are there. For example, the Earth rotation, altitude variability, pitch, variation, and so on. And the spacecraft velocity, but these are generally corrected from the ground station itself. So all of these things are not supposed to happen. The ground stations are supposed to manage these things, but sometimes, in some days and some hours and some minutes and some seconds, these errors do occur. And unfortunately, if these errors occur, we have to live with that. We can't do much about it. These data sets have to be discarded because they are generally not usable. Okay, so all of these are shown here. I hope you know that the yaw, roll, and pitch variability. The yaw is the rotation of the spacecraft about the vertical. Roll is the rotation about the axis of the flight, and then pitch is the rotation across the axis. So there are different kinds of variability. Normally, as I said, satellites are not supposed to do that, but sometimes they do happen. But the systematic errors, which are related to scanner distortions, which are related to minor mirror velocity variability, or which are related to some sort of a scanning skew, they can be corrected, and they are corrected once the data is acquired, they're corrected and then they are provided to you. So because we can't correct it, because to correct these data sets, you need to know all the sensor configuration, their geometry, and their specification, which are not available to the users. So normally the satellite stations and the agencies which are collecting this data, they have this information and they correct the data before they make this available to the general public. Okay. Now, let's try to understand a couple of, but there are other things which we can do, registration and rectification, for example. So these are, very similar sounding terms, and there are similarities, but I think let us understand the difference between the two. So registration is when you are trying to reference one image to another image of a similar geometry, for example, right? So of the same scale. So idea is that you are trying to make different kinds of images, and they are trying to register on top of each other, because each of these images may contain different information which you would like to exploit. So what we does is that it aligns all the images or maps to a single reference layer. So you make one as a base layer, and then you register all the images on the top of that. But then the rectification is a process by which the geometry of the image is made planimetric. So remember that the images are slightly curved because the Earth is curved. So basically, you need to project these images to a reference coordinate coordinate system or projection system, as we call it. And therefore, you need to do some transformation of the image to a coordinate system. So this is what I was trying to talk about. So the UTM or our lat long system has to be projected. So image has to be projected to that kind of a system. Now, both registration and rectification involve very similar processes, right? But remember that they are slightly different in the context. So registration may not involve rectification, but rectification would involve some transformation, of the images as well. Okay. Now, so therefore, there are many references, to rectification may also apply to image trans registration as well. So I'll deal with this kind of issues in a minute. So let's talk about the geometric registration first. Okay. So the first thing is that you might want to do an image to map registration, right? You have a satellite image, you have some other maps, for example, a topographic map or any other land parcel map or anything. And for that, what you need to do, you have to identify the common points on the image and on the map. And then these are called the ground control points. And then you match them to the true positions, right? And then you have to have the true ground coordinates of all of these points, either in the paper or in the digital format. And then you assign those points, those coordinates, and then you register them together. That's a simple, way. The other way, in the other times, we might have to do an image-to-image registration where you are only registering one image on the top of each other, and you may or may not require to assign a geographical coordinate system. Or they may already be assigned to that. So these images may already have a coordinate system. You are only trying to register them together. Again, the process is very, very similar. You just identify the similar points on the two images, and then you assign, you identify them, basically, right? Now, to do this, once you identify the common points on the two sets of data, you have to perform some sort of a transformation of the image. You have to keep one of them as a base image, and the other image has to be transformed. And there are various kinds of transformation we can use. Simple one is a plane transformation. You keep the line straight. This is a first order transformation. You can also perform a polynomial transformation of several orders. Normally, we don't use a very high order transformation, but higher order transformation that do not necessarily keep lines straight and parallel. Sometimes we also do a triangulation, or sometimes we may have to apply different transformation to different parts of the images, for example, right? Or, for example, if the area is very large, you are working on a district or a state scale, and therefore you may not have you may want to apply different transformation into in different regions, because the topography, the setting of different parts of the image may be different, and therefore you want to apply different kind of transformation as well. So these are called piecewise transformations as well. So these are different transformations being applied to different terrains depending upon their nature. So that's the geometric registration process. Then the rectification process, as I said, they are similar, but they are different things. Here we are trying to assign a coordinate system to the image. So here we collect the ground control points using standard methods of, and then we identify these points on the image. These are called type points. And then we transform the image pixel coordinate system to using a mathematical function. And then so basically remember that original image on the image, they only have each point is identified by a row and a column number, right? That's all. And each row and column number has some, some value. But you now want to assign those rows and columns to lat long and latitude and longitude positions, or let's say UTM coordinate system and so on. So basically, you do this kind of a simple equation: x is equal to ax plus by plus c, and and then you solve these equations by putting the values of the ground control points, and then you resample the pixel values from the input image to the newly georeferenced image. So basically, the values of the pixels will then transform to the coordinate system in the new rectified image, right? Again, when we are doing the geometric rectification, apart from the coordinate system, you may also change the pixel size and pixel values. And so in a way, this process is called resampling. So you're actually resampling the pixels as well. And there are many types of resampling which can be done. One is basically called the nearest neighbor sampling. So you assign, for example, the value of this pixel, this is a new pixel now. You assign this value based on the nearest pixel. So there are 1, 2, 3, 4 pixels which are nearby, and this pixel will be assigned with a reference to the shortest distance available from the known pixel value. This pixel will therefore attain the value of pixel number 1 and not of 2 or not of 3 and not of 4. That's a simple one. The other way is to do a bilinear interpolation. This pixel, for example, can be assigned by taking a distance weighted average of all the 4 pixels. So this is sometimes people prefer to use that because that averages out, that reduces the bias. This pixel might have very different brightness value, for example, compared to this and that, but this pixel will only attain that. So that's a disadvantage. So if the terrain is inhomogeneous, if we expect that there are different brightness values of the nearby pixels, then we will prefer to use a bilinear interpolation. The other and a more complex transformation is called cubic convolution, where you fit a polynomial equation to interpolate a surface. And we typically use about 16 pixels, and then the new pixel will basically attain a value from this kind of a cubic convolution process. So these are slightly more complicated, but these are again although I'm talking about it, but these are fairly standard routines which are available in any image processing software. So all you have to do is to press a button. But I just wanted to let you know that there are what is the basic science and mathematics behind that as well. Okay. Now, once you have done all of that, the first thing you want to do is to display the image, right? As I said, each image is basically a raster data, and everything is divided into different pixels, and every pixel has a value. Now, the original raw data, each band basically has a radiometric, depending upon the radiometric resolution, it has a grayscale value. So each band data is basically, is nothing but a black and white or a grayscale image. So if you have an 8-bit display, you will have 5256 gray levels. If you have 11-bit display, then you have 2047 gray levels. We talked about that yesterday as well. So a simple display of a single band data is a panchromatic, is a monochromatic display of the spectral band, where you will see a bright, the black and white image, where the brightness of the image is proportional to the reflected energy, which means that the 0 value represents the darkest part of the image, and 256 value will represent the brightest part of the image. So that's a simple display. Most of the time, these kind of displays are not very useful, and therefore we would like color. We always like colorful things, colors and so on. So therefore we would like to use the colorful images. So how do we convert these images into colored images? Okay, so this is where you might remember the stimulus color theory and RGB color display. I'm sure all of you are familiar with the color concept. There are only 3 primary colors, red, blue, and then green. And then there are complementary colors, for each of them. So there are complementary color pairs. So red, cyan, green, magenta, and yellow, blue, for example, blue, yellow, for example. So these are complementary color pairs, as we know. Now, what is the concept of this, the stimulus color theory is that the human retina has only 3 types of cones. And the response of each type of cone is a function of the wavelength of the incident light. Okay, and typically there are 3 peaks. One is at 400 nanometer, which is a blue color. While the second is a 545 nanometer, which is green color, and then the third is a 680 nanometer, which is a red color. So that is where the concept of the primary colors, red, blue, and green, comes, because the human retina is the most, is most susceptible to identify these 3 different colors. And remember that, it is actually on the same concept our color monitors are made. The TV color monitors, again, they generally have only 3 color guns, RGBs. And now, of course, there are other technologies of LEDs and LCDs and so on. But typically, all color monitor, they're supposed to have 3 color guns, and then all other complementary and second and non-primary colors can be generated by different combinations or combining different proportions of the primary colors. Okay, so basically what I'm trying to say here is that these are, RGB, the red and green and color and blue color bands are then combined together, and then they generate what is called as an RGB display. So the images which you see on your TV screen or remote sensing image, for example, is nothing but how the different bands are coded in different colors. So red band is coded in red, a green band is coded in green, and blue band is coded in blue, and then you generate the RGB display here. So this is how this is similar to the color monitor concept. All the remote sensing image processing techniques also work in a similar way. Okay, so therefore, to get a color image, we use multi-band data. Okay, obviously we can't use a color image from a single band data. So there are different bands of data. Let's say we have 4-band data. Band 1 is blue, band 2 is green, band 3 is red, and band 4 is near infrared. So remember we talked about the electromagnetic spectrum and the bands in which the data is being collected. Now what we do that we color code each of these bands in different colors. So here when you color code the same band in the same color. For example, blue is coded in blue, green is coded in green, and red is coded in red. Then we generate what is called as a true color composite. Okay. Sometimes the true color composites are not very useful. Okay, they sometimes to map and to identify certain features, they're not very useful. Again, this has come from a lot of research on that as well. So we generate what we call as a false color composite. Now, false color composites can basically means that you're not coding the same band in the same color. So for example, here, you can see that, the green is, RGB is coded in different colors, basically. So you can see that all the vegetation colors are here. The red colors are actually vegetation, and therefore they are being coded in red color as well. So so different bands are different, are coded in different colors. I can see a hand here. If somebody has a question. Okay, I'll proceed. Okay, so basically, in the false color composite, you can actually code anything in any band, in any color, but depends upon your purpose, basically, right? So here, the infrared band, has been near infrared band has been coded in red, and the red band has been coded in green, and then the green band has been coded in blue. Okay, so you generate, basically, because we know that the vegetation has the best response in the near infrared band, and therefore we have coded in red. So all the red colors here shown here, they are basically the vegetations which are basically shown here as well. So depending upon the purpose, you can design the different kinds of combination. So here are some more examples of the color composite. So this is the false color composite. It is called a false color composite because the colors which you see here are not the real colors. Okay, vegetations are generally green. This is why you see the green color here are in the true color composite. All the green color shown here are actually vegetation. All the blue color, dark blue colors are water, and then all the white colors are basically sand. So this is the true color composite. But here in the false color composite, the vegetation is shown in red. So people who work with the remote sensing data set, they get used to we normally work with the false color composite because we normally want to enhance certain features and so on. So we get used to this kind of false color composite with time. Okay, now you can, okay, I can see some chat. Right. Okay. Now, so therefore, there are many ways of color image display. So as I said, there is a panchromatic or a monochromatic display. You can also, you can also display a black and white image in color. I'm sure you must be remembering, in old age times when, some of the photographers would color, the black and white image as well. So this is almost like that. Okay. So this is just that, the color, this is the color display of the black and white image, but this is only one band data. Okay. And then you can, superimpose these two images, and then you can map certain features like this. All these things here are probably vegetation patches which are mapped up, like that here. Okay. So these are, these things are done when you have limited data sets and you have limited opportunities for processing the data sets as well and so on. Okay. Now let's proceed, and talk about certain image enhancement, techniques, for example. So the first enhancement technique I'll talk about is a contrast stretching. Okay. So in the contrast stretching, what we are trying to do, as I mentioned before, that we are trying to modify the original histogram of the DN values. Okay. And there are various ways of doing that. The simpler way is a linear contrast stretching, where you simply stretch the histogram, like this. So this is original data, and you stretch the histogram to cover the entire range from 0 to, let's say, 256 of that. And so all the, data sets are basically stretched here. That's a simple linear stretching, method. Sometimes we can do a piecewise linear stretch. So we can stretch different parts of the histogram differently. So, for example, this, that, and then this again, right? So this is a multiple linear stretch, or which is also called a piecewise linear stretch of the data set. And that sometimes is useful for enhancing certain features which are occurring in certain, wavelength ranges and so on. The third type is a thresholding, which is basically a very special case of PLS only. And here what we do that we convert the images into a binary image. So for example, we want to map water and non-water area. So we apply a thresholding. So every data which is beyond a certain threshold will be called as 0, and the other ones will be called as 1, for example, right? So then, if you decide the threshold properly, you can separate, certain features like water, which has very distinct signatures and so on. So these are only to map certain features, in a more precise way, etc., and so on. Okay. And there are some more, contrast stretching methods. There are logarithmic stretching, which can be done, which is useful for enhancing again certain, differentially enhancing the low values and the high values. There are exponential contrast enhancement. There are histogram equalization, for example. The histogram equalization, what it does that, in this, technique, the new image will have a very uniform density of pixels. So therefore, the DN values will become equally frequent. Okay. So typically what happens that in this kind of stretching, the middle values are stretched more. You can see that the middle values are stretched more compared to the lower values and compared to the higher values. So that's a very special type of histogram equalization. It is not very suitable for remote sensing, data sets, but sometimes we use this as well. The other process is called density slicing, where what we do is that the original, the old grayscale is subdivided into different ranges, like this, and like these. And then each, range is then assigned a particular level, in the new grayscale. So there are basically steps, so each range is divided, and then each range is divided, is assigned a particular gray value. So this will result into some sort of a very, broad scale classification of the image itself. That's basically called density slicing. This is useful when you are, it's almost like drawing a contour map. So you want to separate the major classes, and that's it. You don't want the details. You want to separate water, sand, vegetation, etc., and so on. So that's one we needed. But if you need high details of the information, then you have to use other enhancement like the logarithmic, exponential, or the linear contrast stretching, as we talked about. Let me show you some examples. I'm not sure how clear these images would be on your screen, but this is a contrast stretch image, after applying histogram equalization, and this is after linear stretching. So we can see that, in the histogram equalization, the image is, kind of whitish. You don't see a very good contrast. Whereas in the linear stretch, you can see the contrast. You can see that there are rivers, there are floodplains, there are vegetation patches, dark patches, and so on. Okay, those details are missed out here. It's like a whitewashed images and so on. That's why there are differences in that as well. Then, we also use a technique called image filtering. where we try to filter out the high frequency data and the low frequency data. So now look at this is the raw data here. That's how the raw data will look like, for example. Now in the raw data, there are two components. There are certain components which have a high frequency information like this, and then there are low frequency information as well. Now, what we do that we try to use certain processing methods by which we can enhance or subdue certain information. So what we call, for example, we say something like a high pass filtering. So all the high frequency data will pass through this filtering, and a low pass filtering where the low frequency data will pass. So high pass filtering basically will result into enhancing of certain edges, right? And low pass filtering will basically smoothen out the images. So again, there are different purposes of doing that. High pass filterings are typically used when we want to enhance certain topography, certain landforms or lithology, contrast, vegetation, soil, etc., and so on. And all the linear features like lineaments, for example, vegetation corridors, the mountain, elevation breaks, etc., they can be very easily highlighted. And they will reduce the gross illumination differences, basically, right? But the low pass filtering will basically make the image much more smooth. You don't want to see a lot of detail. You want to see a nice picture of the whole area and so on. So there are different purposes for which we can do. I can show you some examples in the next slide. So here, for example, this is a raw image where you don't see, you see some things, you see some rivers passing by, etc., and some features and so on. And on this, we have applied the edge enhancement, which is the high pass filtering. And you can now see that there are, I hope you can see that there's a road, going on here. There are certain, features like these. There are all the linear features in a particular direction are enhanced. These are further enhanced if you produce a fusion of filtered image with the raw image, and you can now see certain interesting features. For example, this is a river bend. You can see there are large oxbows, and so on. Again, there are river bends like that. There are roads which are highlighted here. So all of these features where there's an edge, they have all been enhanced in that features. So these kind of techniques are used when we want to map certain features like roads or like barriers, like the river lines, etc., and so on. That's basically when we use the filtering technique here. Then many times we also want to transform the images, in different ways. For example, we want to enhance the the noise and the signal to noise ratio, for example. So we can add certain weightage to the image, and this is called an addition. So every image, every pixel of the image has been enhanced by certain factors. You can add a weightage factor to that. Similarly, you can subtract the you can do a subtraction as well, and sometimes, so again, you add a weightage to each and every pixel, and then you subtract those images as well. Now, this is basically what is used to detect any changes. So at any pixel which has undergone any change, then you will see the difference. This is almost like image differencing, right? So you're subtracting one image from the other image as well. So then there are multiplication, which is used for masking and image modulation. Then you can produce ratios of different bands of data. This typical ratio which we use is a vegetation index. We talked about that yesterday. And these are again used for selectively enhancing certain spectral features and for suppressing the topographic shadows as well. So there are many useful indices which we can derive out of the ratioing as well. Again, some examples. These are image differencing methods. So for example, we use a Landsat TM T3 band and subtracted this from TM1, so TM3 minus TM1. And again, from our experience and from our research, we know that this kind of differencing image can generate information on iron oxide features, for example. Then TM4 minus TM3, they can detect the red edge features of the vegetation. TM5 minus TM7 can enhance clay minerals, for example. And then you can combine all of these image difference images into a single FCC, for example. So this is what is shown here. This is, this is the, these are different, different images. This is the TM3 minus TM1. This B is TM4 minus TM3. C is TM5 minus TM7. And this image is a false color composite of all the three images. So here, now that you know the basics of each of these, you can now see that the red colors here, which is basically coming from here, they will represent the iron oxide features. The green color here, TM4 minus TM3, they will represent the red edge features of vegetation. And then the blue color here are basically representing TM5 minus TM5, TM7, and therefore they represent the clay minerals. So such kind of methods are used to map different features on the single image. So because we know the basic principles here, so we could combine these images and we can map these features quite nicely in such kind of image referencing methods. Then image multiplication. Again, as I said, you can multiply 2 pixels of the images. You can different from matrix multiplication, and therefore the resultant image will have a much larger DNA range, right? So if you, for example, if the two images are 2 pixels have values of 50 and 50, the new image will have 50 into multiplied by 50, and then we rescale it basically, right? So that's how we do it. So basically, what it does, it actually modulates certain features like the topographic feature, for example, and then we can color code them as well. So here, you can see the color-coded classified images, and then the intensity modulated images as well. So basically what we did, we had a classified image, we have a panchromatic image, and then we use them in intensity modulation. We multiplied the classification image, the red band with the panchromatic image, red R into I, G into I, and B into I, and then we combine each of these images into a color composite, which is what you see here, for example, right? So here, these two images are different in the sense that these are simply color-coded images, right? So every band has been coded in different colors. So you can see that there are certain features, but the boundaries of each of these features is not as sharp as you can see here, right? So therefore, this is a better image. This is an intensity modulated image of that, and therefore we can see the features much better, and we can map the features much better here as well. Similarly, image ratioing. Ratioing is again a very useful technique. I just showed you some examples, same example again. The only caution here is that when we use image ratioing, we have to be careful about the zero values. There are certain pixels in the image which might have a zero values. The problem is that if you take those images and those pixels in the denominator, then you will basically get an infinity value. So therefore, before we apply any image ratioing, we must change all the zeros to 1 or shift all the values by 1, for example. So for example, the 8-bit image, which will originally have a pixel value of 0 to 255, can be converted into 1 to 256. This is a fairly normal practice to do it. In fact, even without the image ratioing, we normally prefer to convert this into 1 to 256 values and so on. And then we can use these images for selectively enhancing the spectral features as well. So these are different image ratioing. As I said, you can combine the different ratio images into a single color composite to get the integrated information out of that as well. Okay. There are some comparisons. So for example, this is an FCC of the difference image, and this is an FCC of the ratio image as well. So you can see that in certain features are looking better here, and certain features are looking better here. So people, try to use different kinds of combinations of different images, and depending upon the purpose, they use these images to map certain features. You can also use both of them to map different features, separately, and then combine the data sets together, for example. Okay, let's now move on to certain other index derivation. For example, there are many indices which we derive out of the digital data sets, and one of the very common indices we talked about yesterday also was NDVI. So the NDVI, is primarily a ratio image. You can see that this is a ratio between NIR minus red divided by NIR plus red as well. Okay, so NIR band minus red band divided by NIR band plus red band. So this is basically a ratio image of that, and so you can. There are many other variants of the NDVI as well. So there's another variant which is used as well, and so on. And then you can convert that into specific data sets. For example, you are using a Landsat data or IRS data and so on. Similarly, we have something called an iron oxide index, which is again red minus minimum red, blue minus minimum blue plus one, etc. and so on. So people have been people who work on this kind of data set. They have designed various kinds of indices for different purposes. So there is a clay index, for example. There are simulated reflection color composites and so on. And then, depending upon your purpose, you can design different indices and then generate integrated data sets for deriving the information and so on. Okay. So here is an example of a vegetation index, which is NDVI. So NDVI, values here, you can see that now what you're looking at is an image, of course, but each image has now been color coded in terms of the values of the NDVI. Okay, so each pixel has a value, anything from basically NDVI values will range from +1 to -1, and so these are the values here, for example, right? So each and typically higher values of NDVI would mean denser vegetation, and lower values will mean the lower vegetation, etc. and so on. Okay, so here, for example, you can see this is actually a river. The blue color here is actual river, which is almost a zero value. So all negative values are basically the areas where there are no vegetation. Okay, so all of these areas, blue and the whites, are basically the areas of no vegetation, and all of this is a very low vegetation. So practically, these are the area, these are the values. The yellow, the light green, and the dark green colors are basically those which are vegetated areas as well, and so on. So this basically helps us to, this is of course a flat, agricultural alluvial terrain of the Ganga Plains. So you don't see a very dense vegetation here, but in the forest areas, you can actually use this kind of data set to even map the density of the forest as well. Now, let's touch upon another technique which we often use, which is called the principal component analysis. Now, what happens that when you increase the band of the data, 4 to 10, 20, 30, 40, bands of the data, you also have the information redundancy. Each band is not very unique. There will be repetition of the same information as well. So if you are playing with different bands of data, then you are also, and if you want to reduce the information redundancy, then we apply a principal component analysis, which is a very commonly used technique for mathematics. So what we do here is we build a new set of orthogonal axes. We combine all the data sets. It doesn't, by the way, in the principal component analysis, we can combine anything. We combine all the bands data, sometimes some other data sets as well. And the idea is that we reduce the data dimensionality, we condense the topographic or spectral information. We sometimes use it for improving the image color representation. We also sometimes use it to enhance certain spectral features as well. And then we display each of the PC band, so basically from, let's say, 10 band data, you have generated a 3 band data, BC1, BC2, BC3, which has least duplication of information. And then you use these 3 bands to generate the principal component analysis bands used for Falk-Hull composite, for example. So for example, here, the original data, maybe they had 10, 20 bands. This has now been, converted into PC 6 band data, where I think most of the information will be contained in the first 2 or 3 bands, PC1, PC2, and PC3. And by the time you reach PC5 and PC6, there's very little information on that as well, right? And then what we do, that we create a color composite of the PC bands, and then we use those color composite for deriving certain information as well. Okay, so here is an example of the different color combinations of PC bands. So this one is a PC435 in RGB. Then the B is an speciated color composite confirmation. And then there are only PC2 being used, only PC3. So there are many combinations you can use to derive these color composite information. You can see this is a much nicer image, than any one of these, because we have used PC4, 3, and 5, and we have coded them into RGB, the red, green, and blue, for example. Then we sometimes use image fusion. We can combine the data set from different satellites. For example, LIS3 data can be combined with PAN data. This is a low resolution data. This is a high resolution data. A limitation here is that is the monochromatic data. This is a multispectral data. But combining the two, we can enhance certain information. So you can there are different kinds of combinations of fusion which we have used here. Brovie, multiplicative, PCA, wavelet. So the idea is to enhance the information by combining the different data sets here. Here again, this is an image of Dehradun area, for example, where we have combined the IRS data and the Landsat, Landsat and spot data, and many features have now been enhanced. You can see that the same window is shown here, and you can see that how clearly you can see each and every river, the floodplain areas, the mountain high elevated areas, and so on. And then we use them for different kinds of mapping exercises and so on. The last topic I want to touch today is classification. Now, after the image processing, we generally need to classify the images to into certain specific feature. For example, you want to create a land use land cover classification, or you want to create a different kinds of vegetation classification and so on. So there are many methods of classification schemes. Again, this is a very detailed topic, but I will just simply talk about two very different methods: supervised classification and unsupervised classification. In the supervised classification, we are supervising the classification and we have some prior information about the area. So we select those areas. We provide some information to that image. Okay, this is water, this is vegetation, this is land, this is sand, etc. And then we ask the computer to apply the algorithm, and then we classify the image. In the unsupervised classification, it's a very simple clustering method. So we ask the computer to cluster the data into 10, 15, whatever clusters you want, but we don't know what those clusters are. For example, we only want what are the different types of the spectral clusters we can generate out of that. So typically what we do, that we generally start with an unsupervised classification to see how many clusters I can see, and then I supervise the individual clusters to generate a supervised classification of that as well. So for example, I have shown you many images, right? Now, this is not an image. This is a classified image. This is actually a land use and land cover map of the image. Now, by looking at the raw image of any given area, you cannot, most of the time, you cannot tell me what is this feature, whether this is a forest or is a water or it is a agricultural land and so on. But looking at this map, not only I can tell where is what, I can also calculate how much area is actually covered by each of the classes and so on. Okay, so the classified map therefore adds a lot of additional information to the original raster image, and therefore it is very useful to have that. Okay. So this is, and the other thing which is other very common use of the classified maps is that you can also monitor the dynamics of the different classes. For example, one can generate a change in one class into another. So this is, for example, a map of the Chilika Lake in Odisha, where you can see that this is the lake water body here, and the catchment of the Chilika has all of these classes: agricultural land, forest area, settlements, and so on. And then if you want to monitor and map how the individual classes have changed through time, then you can generate a time series data. You can use the satellite data of different time periods, and then you can generate the land use land cover map of different times, for example. So here there are maps of 1980, 1988, or 2015, and then you can generate the statistics out of that as well, and then tell that which class has changed to what. So you can generate a statistics related to that. You can also generate change matrix as well. You can not only you can generate the total change in the classes, you can also generate information on what classes change to what, for example. So there are multiple uses of the classification, techniques and maps as well. So I'm almost, time. So I will finish up by saying that the digital image processing allows us to enhance the data. The raw data is not usable directly. So you have to apply a lot of enhancement methods. These are very specialized, things to do. But, I just wanted to give you an overview so that you can know that these are possible things and people who are interested, they can follow it up. The choice of the technique, as I said, depends upon their specific applications. But what is important for you is not to blindly follow, even if somebody wants to follow up on this, don't blindly follow the method or tool which is given in the software, but understand the underlying operation, the mathematical operations behind that, because then only you can understand what is going to come out of that and what is the most appropriate method which you should apply to enhance the features you want to enhance, for example. Okay, that's one thing. The second thing is that the interpretation part requires some understanding of the terrain, right? People often think that remote sensing is everything. You can literally do everything sitting on a desktop. I would say no. You can do a lot of things, but not everything. Every remote sensing data interpretation must be validated by ground verification. And therefore, it is not a replacement of the field-based mapping or field-based validation, but it is just a more enhanced way or more a better way. It certainly saves you time. If you have to survey a 100 by 100 kilometer area, you cannot do that. You can do that, but it will take a much longer time if you only depend on the field survey method. But if you do this, this kind of techniques, use this kind of data sets, you can reduce your time and also effort. But then remember that every remote sensing data which is coming out of that, every map which you are producing must be validated in field, at least in a limited way, if possible. Okay. So I'll finish up here, and I'll be more than happy to answer your questions through chat box, etc. I'll stop the share, and I will be happy to answer your questions as well. Thank you. Yes, the first question is about the GIS. We have not covered the GIS part yet. That is my third lecture, so maybe we can wait for this question to be answered. Then the image filter, how much data we can use? Well, there is no limitation of the data. See, the size of the data and the size of the image will depend upon your computer capacity, right? Sometimes people are using a slow computer, a low capacity, then you have to break the image into different parts and then process it. If you process the entire image in one shot, your computer will hang, for example, right? So that is a function of, it's not a function or limitation of the data or the software, it's a limitation from your computer, basically, right? Well, the common points of two images, okay. The fundamental point here is that that the points you are choosing as a control point must not be dynamic. Okay, so you must use a point which is fixed in geometry and in time. That's one. And the second, that it should be identifiable on all images or all maps, for example. That's the criteria which is used. Is the 11-bit have two or it should be, well, the 11-bit data will have the gray colors from 0 to 2047, but if you count 0 also, then it will have 2048. So that's how it is counted. Okay. So the range is 0 to 2047, but the number is 2048. Okay. Yeah, I understand. It's very it was a little complicated, but as I said, the idea was to give you an overview. Send your email ID and phone. My email ID is already written in the first lecture. You can take that from there. How to take up image processing as a career? I'm BSc Agriculture. Well, you need to do a full-fledged course in remote sensing, and there are multiple places where full-fledged courses are offered. There are sometimes you can look for the advertisement at NRSC Hyderabad and ISRO. They keep on running short-term courses. There is an institute called Institute of Remote Sensing in Dehradun. They keep running short-term programs, also long-term programs. So you can register and for those courses as well. Difference between the digital image and the analog image. I don't know what exactly you mean, but analog image is basically a photo. It's a photo. It's like a photo print, and it's like a digital image. Basically, that's all. So that is what it means basically. How can we apply this method to solve real-time problem? Well, yeah, every problem can be identified. So there are many problems related to, for example, mapping the land cover changes, as I just mentioned. There are applications related to flood risk assessment, for example. There are applications related to installation of impact of storms on a given area. There are applications related to river form changes, and there are a number of applications which are related to natural resource mapping. They can be done. How I can precise cost of cultivation in a salt affected by use of remote sensing. The salt thing is a bit challenging, but people have used remote sensing data to map the salt affected soil, because what happens that when a salt covers the soil, it has a very high reflectance. Salt is almost like an ice. It has 100% reflectance. So you can actually map what is called as an Usar land in many areas. So the Usar land maps areas can be mapped by using this kind of a data sets. Drone image processing in principle very similar, but because you're dealing with a very high resolution data, then therefore the softwares and the tools are slightly different, but the basic principles remain same. The satellite image data and drone data are very similar, except that they are very different. They have very different resolution. But yes, as you said, the basic principles are really same. What is false color composite in the remote sensing images? We are calling this as a false color composite because the colors which you see on the images are not the actual colors. For example, vegetation in real life is green, but in false color composite you will see them as red. Soil in the real life can be white, but it will appear as yellow, for example. So that is why it is called a false color. Okay. I have listed the softwares in my last lecture, so please look at that as well. The ArcGIS, the NDVI, and the ERDAS image processing softwares, all of these are listed in the last lecture as well. So please look at that. Okay, I think the questions have dried out for today.
हाँ जी सर, ऑलमोस्ट जो क्वेश्चंस हैं उनकी क्वेरी रिजॉल्व हो गई है। बस आपसे एक निवेदन ये है जी, मेरी आवाज आ रही है आपको सर? हेलो सिन्हा सर, मेरी आवाज आ रही है आपको? हेलो हेलो
Okay, I suppose
रोहित जी, मेरी आवाज आपको आ रही है?
Clear. So let me thank all of you again for your patient listening, and we'll have one more lecture on the GIS. So some other things.
रोहित, मेरी आवाज आ रही है आपको?
Thank you so much, and we'll see you again on.
हाँ जी सर, आवाज आ रही है। शायद नेटवर्क इशू सर, कनेक्ट होगा शायद।
हाँ जी जी, सर को बोलिए। हेलो सर, मेरी आवाज आ रही है आपको?
Sir, you are quite audible.
कोई टेक्निकल ग्लिच है, आप एक बार बोल दीजिए। हाँ ठीक है, आप कंक्लूड करिए ना।
Thank you so much, sir, for such a wonderful lecture. So we'll be continuing with tomorrow also with his proceeding lecture. and we'll elaborate regarding how
नहीं नहीं
they will be further remote
कल
sensing would be.
कल पंजाब एग्रीकल्चर यूनिवर्सिटी के प्रिंसिपल साइंटिस्ट का है, परसों है सरकार 24 में, 23 को कल पीएयू के एक प्रिंसिपल साइंटिस्ट का है एग्रीकल्चर इंजीनियरिंग डिवीजन के, ठीक है।
So hope to have sir with us from on 25th of May. So thank you sir for today's session. Thank you to all the participants for cooperative attitude toward the session. Thank you one and all for today's lecture. Now you can leave.